Well, good morning, everybody, and I wanted to just say thank you. Thank you for the very kind invitation to come and speak. So this morning's talk is going to be a little bit different. So essentially, it really revolves around something that happens to me all the time in my clinic, which is when people come into my clinic and they are well-intentioned, well-meaning, and they have read the latest thing, or they've seen it, or usually more often someone says, oh, I didn't do this, but somebody phoned me up about this, and you kind of go, okay, sure, well, no problem. So really what I want to do is to tackle all of those things that you will have seen, you will have heard, and I think the overriding message is if you heard it first from Google or a friend of a friend, then probably you should investigate further before you go spend any money. You know, whether it's seaweed or whether it's electric shocks to the nipples, whatever it is, you should probably think twice. And really what I want to do is to sort of frame this around, I guess, this concept. The idea that actually you see things and they're not necessarily always as they seem. So let's start with this concept of Mice and Men, a very famous novel, but in actual fact important in the context of what I'm going to tell you about, which of course relates to the fact that so many times you will have seen something or heard about something where it usually, you know, says, look, we've got these fantastic results, we think this is going to be great, and then you read the small print and what you realize is that 6 mice have been tested with some kind of drug or some kind of experiment, and the mice maybe survived. And what this is essentially is somebody wanting money. So this is something I learned when I was back in Cambridge with Roger Barker, and I said, well, you know, what's the story with this? And he says, look, the bottom line is if you're a company, a technology company, and you want investors, what you do is you get together a little bit of data, you plumb it into some mainline media, and it's much easier, of course, these days with, you know, online resourcing, to be able to say to them, look, you know, this exists, and what they then do, the company, is they'll go to their investors and say, hey, did you read about our story? It was all across the Sydney Morning Herald and The Age and all of these other places, and they will then generate capital. So this is what you will see a lot of, so please do not buy into it. And the reason is simple. Mice, monkeys, every other animal, rat, nobody else gets Parkinson's, only humans, okay? So in actual fact, every time you see an experiment where they've used a mouse model of Parkinson's, that's what it is. I, funnily enough, have no mice on my waiting list waiting to see me. They may be in the waiting room. We have food there sometimes, they hang around, but they're certainly not waiting to see me. And then I think the other thing I really want to raise early is the notion of whether we really can expect a cure. Now, I started doing research in Cambridge in 2000. And in 2000, what people used to say is, oh, you know, we'll probably have the cure in the next 5 years. Then 2005 came along and, you know, maybe we'll have the cure in the next 5. And then 2010 came, well, we're hoping that we'll have the cure in the next 5. 2015 came. So I'm not sure if anyone's an astronomer and would recognize this, but this is Neptune. So Neptune takes over 60,000 Earth days to go around the sun. So when people tell me, yes, it's going to be available a cure in the next 5 years, I presume that they're referring to Neptune years rather than Earth years. And that's potentially what we may have to live with. Because in actual fact, we have no right to expect a cure. There are very few diseases that we have in this world that we actually cure. You might treat something very well, you might have to then watch people and make sure their cancer doesn't come back or that their diabetic control is good. But effectively the idea of curing something is very, very remote in most diseases in the world, and I think that's very, very true in a very complicated disease like Parkinson's. And then I think what I want to do is to tune you into this thing. And this is a Spruiker warning, okay, or the Spruiker alert. So I didn't know what the word spruik meant until I came to Australia. But essentially, what you need to be aware of is the wording of stories. And we, the researchers, the medical community, are all as guilty as the next person, because we want to try and put out a story so that we can get some idea to the patients that, yes, we're working on something, please keep donating your resources and your time and your energies, helping us with these research things. But then the media get hold of it and they go, well, it's got to be an Australian first or a world first, or it's got to be a groundbreaking, and they put these words in there, and essentially the editorial happens and the story gets lost because, you know, it's usually about 100 seconds of footage. I can tell you that when you see that 100 seconds of footage, they have been out and they have been spent about 4 or 5 hours filming, okay? 4 or 5 hours filming people like myself and my team and my patients for about 100 seconds. And if you look at the 100 seconds of film, it'll be 80 seconds of Sophie Scott or whichever reporter they've managed to send out on the day. And the person who really knows what's going on, effectively saying, well, it's kind of encouraging, he's gone. Sophie Scott or whoever, I'm not accusing Sophie in person. Sophie, you're a great person. Thank you for following the Twitter handle. But essentially, what we really need to do is get you tuned into the language. And there's one word that you need to listen for.
But there is hope on the horizon for those with Parkinson's disease.
And we're hoping it'll enable us to diagnose the disease earlier than we can currently do.
Doctors hope this new research will help identify those patients at risk of hallucinations.
There's renewed hope for all those with Parkinson's disease.
Your phone could be the best hope against Parkinson's disease.
Australian doctors are part of a worldwide trial which they hope will help them more accurately diagnose patients with Parkinson's disease.
Are you getting a theme? Okay, so it's a 4-letter word, cure and hope. And hope and hype are very similar words, but the question you ask, why is the letter Y in there? And the answer is because, in actual fact, hope doesn't mean we're there yet. So what I want to do now is I want to take a little trek through a whole bunch of things that I suspect you may be familiar with, you may have had discussions with your own specialists about, and these views that I will express are generally my own views, and I think that it's important to know. But how many of you, I suspect, will have seen this?
It works most of the time.
In fact, it's...
So this is a police officer who has filmed himself, put it on YouTube, and shown that essentially marijuana helps his dyskinesias. Hands up, who's seen that video? Who knows this police officer? Fantastic. So you've seen these very dramatic videos, and then him just sitting there calmly. In fact, he's not just sitting there calmly, he's stoned. He is lying back on a chair like this, going, oh, I feel so good now. It's all gone away. Let me show you another police officer. This police officer is my police officer. This patient has now passed away, but kindly allowed me to show this video because it makes a very important point. So this is my police officer. Look at him go. Looks just as bad as that officer, doesn't he? He's got all these horrible movements, these dyskinetic movements. And then, what you'll see in the video is that he does this. Is this marijuana, I ask? No. My police officer has never touched marijuana. Very against the whole concept. This is, in fact, the natural course of your disease. So what happens when you develop motor fluctuations, as those of you who may have gone on and had deep brain stimulation or advanced therapies like apomorphine or levodopa, duodopa infusions, is that in actual fact there will be times in your brain when there is too much stimulation going on because the dopamine is in excess of what's required, and there'll be times when it's just right, and there'll be times when it's too low. So in actual fact, I think my video is every bit as impressive as the American police officer, but I can't put this on the web because, funnily enough, it doesn't involve something that's illegal and therefore more interesting, and therefore you want to have a look. But let's have a look at the science, because that's kind of what I'm here to do, not just to rant about it. So we talked about this guy saying, I feel better. Well, actually, this study has been done. So this is actually published. It's published in 2001 in a very leading journal called Neurology, very, very respectable journal. And basically it's there saying cannabinoids reduce levodopa-induced dyskinesia in Parkinson's. So first thing to remember when you're assessing a paper is you go, it's 2001 when it gets published, it's 2017 now, no one's using marijuana as a real treatment. People are using marijuana, trust me, but not necessarily as a real treatment. And the key to this is that it clearly doesn't work. I mean, people have been doing an open-label trial of marijuana for thousands of years, probably. And the fact of the matter is, do you not think we would have realized that it would work before now? But let me show you this paper. And I don't want to labor this paper, but the paper is important for a number of reasons. So this paper only actually contains 9 patients. 9. Okay? We keep saying this disease affects, 1 in 1,000 people. We've got 9 people into this study. In actual fact, only 7 patients made it through this study. It was what's called a double-blind crossover. And what that means is that patients were randomized to either get a cannabinoid or a placebo, and the doctor didn't know whether they were getting the placebo or the drug, and the patient didn't know if they were getting the placebo or the drug, and so that was the game. And it was randomized, so I didn't know what you were getting, you didn't know what you were getting, but you had to have both, the placebo and the drug. Now, the reason only 7 are reported is because when they gave the drug in the first round to 2 of the patients, they couldn't go on and take the placebo. It dropped their blood pressure so low, they had to be resuscitated. They were very unwell. So what about the blinding effect? So now suddenly we're in this control where I say, oh, look, I don't know whether you're taking the drug, and you don't know whether you're taking the drug, and the patient takes something, they hit the ground going, wow, look at those fantastic unicorns. They look amazing. And you go, well, that placebo must be really strong. So in actual fact, it's not a blinded trial. And the truth of the matter is that, in actual fact, of the 7 patients that made it through the trial, 5 of them reported having hallucinations, dropping their blood pressure, feeling a little bit spacey. And so in actual fact, we know that actually for the majority of patients with Parkinson's disease, using cannabinoids is something that may not be the smart thing to do. Marijuana may not be a smart thing to do. Having said that, to my core, I'm a researcher. So in actual fact, I'd like to know. And I had a patient who came up to me and said, I've been using street marijuana. It's made my walking amazing, doctor. So I said, okay, we have a research team here who are incredible. They have resources to do research in marijuana. Why don't you bring in your marijuana and I will get them to make me a placebo to match it. They can do this because they actually have things that taste the same. And basically, this is what happened. So you can see the video before and after he took marijuana and before and after he took placebo. Now, I can't remember whether placebo is across to the right or onto the bottom or drug is, because in actual fact there was bugger all effect. Absolutely none. But the patient swears blind. I'm amazing. And you know why? Because when I ask him, and of course I've logged, and I don't know what he has, it's double blind as well. I said, how do you feel after this? After he took the drug, funnily enough, he feels much more relaxed. So he's not so anxious. And anxiety plays a big part in Parkinson's disease. So in actual fact, it may very well be that there is a role for some elements of the marijuana story. But in actual fact, the idea of going out and taking street marijuana, which is kind of what you'd have to do at the moment, I would suggest is probably going to be more deleterious to your health and more risky than leaving it alone. And using the money for a massage or some speech therapy or some physio, all the things that we know are actually effective. The next thing I want to talk about, because you may have heard of this, is the idea of using ultrasound instead of surgery to treat Parkinson's. So this is real science. So this is work coming mainly out of the States and Europe, where the idea is to use focused ultrasound beams. Now, you'll remember having gallstone treatment about 10, 20 years ago, where people used ultrasound beams to break up the stones, what we used to call lithotripsy. So essentially, if you focus ultrasound energy, you can do damage. And that's exactly what this surgery does. So in actual fact, what it does is it targets areas of the brain. And the studies that have been done so far, I hasten to add, are not published to the same level in Parkinson's disease as they are in essential tremor. So essential tremor, not Parkinson's disease, they publish the results, very good outcomes. But essential tremor, of course, is not a degenerative disease, so it's not going to get worse over time. Parkinson's disease is. Now, many of you will know that before we had deep brain stimulation and we did operations to put electrodes into the brain, we used to just go in there and burn holes, things like pallidotomy and thalamotomy. So effectively, we've been very good at putting holes in the brain surgically for 50 years plus. So in actual fact, what this ultrasound does is it does exactly the same. But what that means is once you put a hole in the brain, there is nothing you can do afterwards. So there is no adjusting it up or adjusting it down. It is done. So I think the fact of the matter is that this may very well be a reasonable therapy for a small number of patients, where you say, look, this person is not suitable to have a surgery, they're not suitable to have any of the other advanced therapies. So we can actually say, look, this is going to be a reasonable thing. But I don't think that people should be sitting there thinking, well, I'm going to wait until we've got this technology ready and sorted here, and I'm not going to have treatment X, Y, or Z. So in actual fact, I think this is a reasonable thing to be looking at, but I don't think it's the next best thing. It's not a cure, okay? Important to know. And then I want to come to this. Now, I think it's this weekend. The Australian newspaper has a weekend supplement thing, and I think they're going to do a feature on this story about near-infrared light. Now, I didn't actually know Senator Williams before the newspaper phoned me up to ask me to comment on what we're about to discuss. But some of you may well be aware, hands up, who knows this Senator Williams story? Yeah, absolutely. There's a few people in the room. So essentially what Senator Williams read and heard of was some research in Sydney where effectively people were beaming infrared light, so not laser beams, but infrared light into the brains of mice to try and improve a model of Parkinson's. Now, do you remember some of the things I mentioned? Okay, so model of Parkinson's, mice, not very different, okay? Very different. And essentially, what Senator Williams has done is he's constructed, I think with the aid of Bunnings, we're not marketing, are Bunnings a gold sponsor this year? No. Okay, next year. Some infrared light inside a bucket, apparently over his head. I haven't spoken to Senator Williams, and I understand that all of the things he's doing are the best interest, but the problem is that this story gets out, and then people hear that Senator Williams feels like he's doing very well. And then they go, well, I should go and get a bucket, and I should do this. But before you go rushing off, let's have a look at that paper that came out of Sydney from my colleagues. John Mitrofanis is on there, I think, senior author. And what he says in this paper, by the way, they also did this model in Alzheimer's mice. Again, mice don't get Alzheimer's either. But it seemed to help the Alzheimer's mice too. So they have no idea how this works, but they do believe that there are some benefits, there are some protection of the cells there. But the fact of the matter is, there is no human research. And what the guys in their paper, actually say is, look, the penetration of infrared light from the outside of the skull might get you to within about 2 centimeters inside the human brain. But unfortunately, the problem with Parkinson's is about 5 centimeters away. So in actual fact, the chances of this working just by putting a bucket on your head are probably limited by the technology. Now, this isn't a fanciful idea, it's not a crazy idea, as I explained in my interview to The Australian. And the fact of the matter is that Professor Benabid, I think it's in Grenoble in France, who was the pioneer for deep brain stimulation surgery, is looking seriously at implanting effectively laser beam delivering infrared lights through a device implanted in the brain. But that's going to be a surgery again. But it's a very reasonable thing to do. But I have to say, I don't know that I would go volunteering to have that as an approach just yet. Many people may not be aware of the Nilotinib story or Ticinia story, but essentially you may be familiar. About 2 years ago, a story broke about a chemotherapy treatment that might help with Parkinson's disease. And this study came out of some very good basic science work where, again, people were using this drug, Nilotinib, which essentially is used in a bunch of blood cancers in treatment at the moment. They used it in, I think, a rodent model of Parkinson's disease and showed that it might help the cells to survive. But the next thing that they did, which was a little bit weird, was they went straight to a human trial. And the human trial seemed to be not very well constructed for those people who look at human trials all the time. And they said, we're going to do a mixture of patients. So you can have Parkinson's or dementia with Lewy bodies, Lewy body dementia, which is like having Parkinson's, but it's an accelerated process, like having Parkinson's on speed, if you like. And they gave patients this chemotherapy, and then they reported as an abstract and then subsequently as a paper meaningful clinical improvements in these people. And they said that these improvements were in terms of falls and cognition. What's interesting is that they reported that 10 out of 12 patients were better, but they reported none of the actual results to say what they improved on. And also, of course, this is an unblinded study. Everybody knows who's getting what. Patients know, and the doctors know, which means we now have 2 sources of bias. The patients get a placebo effect, which is very real, and strangely enough is carried by dopamine. The dopamine in your brain is the thing that helps the placebo effect. The other being the doctors. I've got this new treatment, I've put a lot of effort into it, I'm going to give you the treatment. You look better to me. You do look better to me. So you now have this unblinded issue. They did have some reports of some biomarkers, but I have to say, biomarkers from spinal fluid in Parkinson's do not seem to be a robust marker of the disease. They vary across labs, they vary across the time you take the spinal fluid. But effectively, this has spawned some research. So there is now, I think it's actually a trial being sponsored by Cure Parkinson's Trust and the Michael J. Fox Foundation, who are actually going to trial Nilotinib in a controlled experiment. And the reason that's very important is because in about 1 in 10,000 people, Nilotinib causes serious heart damage, your heart dilates and stops pumping. So if you were thinking about going out and getting some Nilotinib, please don't. Let's wait until we get the results of the real trial. But at the moment, we're going to deem this as plausible. Okay? Maybe a little bit less plausible is the idea of using growth factor. So one of the things that you'll see, it's a bit like spruiking, is that you'll see studies being published in two sets. So the idea here is to say, look, we know that there are certain chemicals, what we call growth factors in the brain, that can, if you like, allow cells to grow. If you like, fertilizer for brain cells. Okay? And the idea here is to say, well, if we could put that chemical, maybe using some kind of virus to carry it along for us, so it gets close to the area of damage, so we have to do an operation, put it in, and then hopefully it'll work as a fertilizer for those cells that are dying, maybe we could improve Parkinson's disease. And what they did was they did a nice thing where they published the first paper saying we did the procedure and it was a great success. But the success was surgically, we put the stuff in the right place and nobody had any serious adverse events. They didn't speak at all about what the drug or the treatment did until about 2 years later when they'd had time to follow the patients up and see whether there were any improvements in the physical Parkinson's. And the answer is there were none. Absolutely zero. And interestingly, with my work in the brain bank, the reason there was probably no real benefit here is because in the patients they selected, there were no cells remaining. So this is like putting fertilizer on a field with no seeds. So it is never going to work. So this treatment is probably busted, but at the same time, if we were to take patients at a much earlier stage and do this treatment, it might add benefit. We don't have that data, but people have suggested this is what we should do. Now I'm going to move into another treatment which is very hot and very topical, and this is a diabetes drug. And why treat Parkinson's with diabetes drugs? And the answer is, well, we're not entirely sure, but we do see some relationships between energy, use, consumption, diabetic control, and the brain in Parkinson's. And interestingly, there is some epidemiological evidence to link Parkinson's and diabetes. That is to say, if you have got Parkinson's disease with diabetes, your Parkinson's is usually a little bit worse, unless you keep your diabetic control very good. So if you have bad diabetic control, your Parkinson's is a bit worse. Exactly the same for Alzheimer's, exactly the same for vascular dementia. So in actual fact, probably no surprise, and probably a general thing about how your brain measures energy or works properly to try and get the thing working properly. And they have done some mouse model work to see whether this diabetes drug in a mouse model of Parkinson's might slow cell death, and the answer was yes. And that was enough to spawn a trial done by my mate Tom Faltony, where we were together in Cambridge and now looks in London, where he looked to see in just 45 patients whether there was any benefit of using this drug. Now this is an injectable drug for diabetes, it's not cheap, but effectively this was Tom's first effort. So what he said was, we got 40 odd patients, half of them are going to get the injection and half of them won't, and so then we'll be able to see whether there's anything in it. And the truth of the matter is that there was some benefit. In actual fact, the group that had the treatment seemed to be better on a physical rating scale and seemed to be better on a cognitive rating scale than the people that hadn't had the injection. But of course, this was an uncontrolled trial. Again, the doctors and the patients knew who was getting an injection. So in actual fact, it was a little bit harder to judge. But it was enough, really, to sort of say to people, look, I think we have something here that is plausible, just plausible. Let's go and do the proper trial. Okay? So the proper trial is to say, okay, now what we need is we need to have a randomized, so you don't know what treatment you're going to get before you go into the trial. Double blind, so you don't know what treatment you're getting, I don't know what treatment you're getting all the way through the trial. Placebo controlled, so there's now a placebo. So everyone is injecting themselves with the diabetes drug or injecting themselves with the placebo. So now you've taken out that placebo effect. And this study just came out, I think, about a month ago. Thankfully, I was overseas when the story broke. I've been telling all my patients about this study for ages because I knew the results. And then I went away, and then the story broke, and it was great because nobody could get hold of me. It was fabulous. And this was published in The Lancet. So The Lancet, as you probably are aware, is a very famous medical journal. It doesn't publish rubbish, so this is a very, very reasonable study. And this is the key part of this trial, okay? So the graph on the right is the graph I want you to just keep looking at while I'm talking. So the top line is what happened to the people with Parkinson's who took the placebo. And you'll see that red line just keeps going up gradually. And that is a worsening of their physical Parkinson's over the course of the trial, which was 60 weeks. You'll see 60 on the bottom line. You'll also see a point 48 weeks. And 48 weeks is how long they had the treatment. At the end of 48 weeks, they stopped taking the drug to allow for what we call a washout, to see whether any effect may have just been a symptom-relieving effect. The blue line is the treatment group, so the patients who injected the diabetes drug. And what you will see is the blue line doesn't go up, it goes down. In actual fact, at the first checkpoint, which I think is 12 weeks, you can see that the biggest improvement has happened. And then it stays flat, and then there's a little bit of a tail that goes up at the end when they stop using the drug. So what you saw right at the end, which is the primary endpoint, is that the blue line and the red line are separated. There is about a 3-point spread between them. This is when patients were not on their medication, having taken it away overnight. And this is a statistically significant result. Interestingly, when you gave patients their drug, that effect was masked. So there was no difference if you gave them their treatment. But effectively, this suggests that there might be something in this disease-modifying story. But there are two caveats that I point out. One, in that blue line at 48 weeks, what you'll see is there seems to be a deterioration when you take away the drug. Well, if this is a neuroprotective drug, I don't quite understand why it should work so quickly. And two, if you look at 12 weeks, most of the effect has happened in 12 weeks. Well, if this is a neuroprotective drug, slowing cell death, which we know is slow, why do they suddenly get better at 12 weeks? It doesn't make a lot of sense, unless this drug may be actually improving symptoms, and as I said, better diabetic control in people who have Parkinson's and diabetes is better for their Parkinson's. All of these patients were non-diabetic, okay? So it's difficult to know, but essentially this now has spawned the idea that we need to do a phase 3 trial. So that will have hundreds of patients in it, and it will be more than just one centre run by Tom. In the meantime, though, we have a problem, because now I've got a whole bunch of people coming up to me saying, I want to have exenatide, I hear it works. So what I did was I caught up with Tom. As I say, we were together in Cambridge, and this is us in June in Vancouver. So Tom, I asked him the question, what should my patients do? And he said, they should wait for the proper trial. He said, what I did was, a little proof of concept. What we need to do now is a proper trial, because, this is just my centre, it's a very small number of patients, might not be true, might be dangerous. So we have to wait. And I think that's important, because this other paper that came out again in a Lancet journal, Lancet Neurology, used another diabetes drug. It actually works through the mechanisms that regulate the diabetes control of insulin. So effectively, that trial was done, again a phase 2 small trial, and there was no significant difference. So if there is something that's happening to control the diabetic thing, it isn't an obviously strong signal across all of the drugs that we have. So I think we need more data. So I want to move away from the exenatide story and move into one of your favourite subjects. Who wants to talk about stem cells? Yes, everyone wants to talk about stem cells. So the most promising therapy we've got, they've been promising now for over 20 years, not delivered anything other than more questions. And I think it's important to know what we mean by stem cells. So what you guys mean by stem cells is you're going to put a cell into my brain, doctor, and it is going to make the 200,000 connections, or however many, that it used to have before it died. When I talk about stem cells, and my side of the crew talk about stem cells, no, we're talking about putting cells into your brain that make dopamine. That's all we're doing. So in actual fact, the best that we can ever hope for with a stem cell trial, and we don't usually really use stem cells, and I'll explain in a second, the best that we can hope for is that we might get you off your medications, we might avoid those dyskinesias and the fluctuations, which would all be good, but we're not talking about a cure here, okay? If your disease was very, very slow, and it meant you didn't need an advanced therapy, and it meant you didn't have other problems, then in actual fact that would be enough. That's great, we'll take that as a win. It doesn't necessarily have to be a cure. And the work we've done so far really hasn't used stem cells. We've used fetal grafts. So what that means is we've taken cells out of aborted fetuses before they were going on to be babies, and we've dissected out the cells that were going to produce dopamine. And then we put those together, maybe half a dozen fetuses, the cells, all mixed up, and put those into patients. And these trials happened in the early noughties, and there were 2 American trials that did this. And they were great trials for lots of reasons, but unfortunately they were both stopped prematurely, because when they put these cells into patients, they developed incontrollable dyskinetic movements. In fact, all of the patients who had the treatment required deep brain stimulation surgery to calm those movements down. Now, the fact of the matter is that hasn't stopped people from looking at stem cells. My old boss in Cambridge, Roger Barker, is leading a trans-Euro project where they're using slightly different cells, what we call pluripotent stem cells, to try and address this issue and, if you like, get a more refined treatment. And even here in Melbourne, you'll be aware of a trial which Andrew Evans is running using what we call parthenogenetic stem cells. And parthenogenetic stem cells effectively are less contentious ethically. So these are essentially cells that are not taken from aborted fetuses, but are harvested in another way from unfertilized cells by an international company. They claim that they can, if you like, produce very pure cells that they can put into the brain and safely treat patients. Now, the fact of the matter is this trial is ongoing. I believe that a number of patients have been done here in Melbourne, but it is not without controversy. And Andrew Evans and I have spoken about this. Andrew and I are friends. I intend very much to remain Andrew's friend. But I know that Andrew has taken some heat over this trial from people like my old boss, Roger Barker, and others around the world, including his old mentor in London, Andrew Lees, who said, look, actually, we're not sure this is a good approach. We're not sure that these cells will actually go on to become dopamine cells. What if they turn rogue? And the answer is we don't know yet. We need the data. I think some people around the world are concerned in case this trial goes badly, and then all stem cell therapy gets tarred with the same brush. But we wait. And then you have to remember that there may be something in this whole idea of stem cell transplants, because what I haven't mentioned yet is patient number 4. So patient number 4 is a Swedish patient who was in the original fetal graft work done in the late 1990s, I think it was. And patient number 4 was the 4th patient who was transplanted. And at that time, they used to do one side of the brain and then go back a couple of months later and do the other side of the brain. So they target the worst side, i.e. if my symptoms are bad on this right-hand side, they'd have to operate on the left. And patient number 4 had the first surgery and refused to have the second surgery because he said, I am cured. He stopped taking his tablets and he did very, very well. And we all went, well, that, maybe it is a proof of concept. And it's interesting because nobody knew what happened to patient number 4 until 2015. I was at a meeting in Fort Lauderdale and met Patrick Brunden, one of the Swedes involved in this trial. And he told us that patient number 4 had just died. Not a big surprise. This is maybe 20, 30 years after the trial. So he died of natural causes with Parkinson's, not from Parkinson's. And we said, well, that's very impressive. One question we want to know is, did he have Parkinson's? And the answer is yes, he did. The brain went to post-mortem and he did have Parkinson's. I went, well, that's amazing. You guys must feel stoked. And they went, well, not really. Why is that? Well, he spent the last 10 years of his life in a nursing home, falling over with dementia. So in actual fact, just replacing dopamine is not going to solve all of Parkinson's. The falls aren't going to respond to dopamine, hallucinations aren't going to respond to dopamine, dementia isn't going to respond to dopamine, so we have to be very, very wary about what we take from that. The other thing that's come out of these trials is something that's really big that I need to tell you about, and that is the question of whether Parkinson's disease is a prion-like disorder. What we're talking about with prions essentially is where the brain has naturally occurring proteins that turn rogue. And the easiest way for me to explain this, and apologies, fold your clothes nicely, put them into a drawer, close the drawer, it works nicely. But if you take the same clothes, you throw them into a tangle, throw them in the drawer, try and close it, it'll jam, and it won't work. Well, the drawer is our cell, and the tangle is our protein. So a natural protein called synuclein or alpha-synuclein in the brain can turn rogue. And the question is whether something can act to turn it rogue and make it go tangly. And the reason this became important is because we know that in Parkinson's disease, there seems to be some kind of spreading process of the disease. People might be aware that constipation seems to predate Parkinson's disease, losing your sense of smell, predate Parkinson's disease, and of course, my favorite, dream enactment behavior can certainly predate Parkinson's disease. And when you follow people who died at different stages of Parkinson's, you actually see more and more spread going through the brain, where in actual fact you say, well, maybe there's something that is traveling from cell to cell, infecting the next level. And you will all be familiar with the idea of prion disease because you'll all heard of mad cow disease. My country's triumph, my gift to the world. But essentially, that is a prion-like process where you ingest something and then, you take, if you like, dead cows, eat them if they were infected, it then gets into your system and affects your brain. So the idea has always been something that's been kicked around, but actually some of the science came from these trials. So I told you about the fetal graft trials in America that were done and stopped early, but those patients continue to be followed up. And what was interesting was that inside the brains of patients who'd had the fetal grafts, they found the same tangled proteins. So these brown balls of protein, what we call the Lewy body, were inside those cells that were put in from, if you like, undeveloped babies, fetuses, who definitely didn't have Parkinson's disease. So what that means is, for Parkinson's disease to get into those cells, it might have come from the host, transfected. And so this has led to a whole range of studies and treatment options, which we're going to close with over the next few slides, where we say, okay, well, maybe we have a disease that might be due to these infective processes. There are a few caveats. Number one, the region of the brain where they put these cells from babies never gets Lewy bodies. Okay? The Lewy bodies occur down in the brain stem, in the substantia nigra, where the black substance, where the dopamine cells are coming from. Where they put these cells is where the dopamine is released in a part of the brain called the basal ganglia or the striatum. And effectively, we don't see this pathology in that part of the brain in Parkinson's. So you already know there's something wrong with this model. And in actual fact, it's difficult to be sure, because in actual fact, we know that with things like Creutzfeldt-Jakob disease or mad cow disease, if you go operating on the brain or doing anything surgical on these people, you have to throw away the equipment because you can infect the next person. You can't destroy the prion. Now, we've got loads of Parkinson's patients who've had endoscopies or brain surgery, deep brain stimulation surgery. You kind of think, well, if we were able to get dirty electrodes, as it were, that have got prion sticking on them, and we put them into the next person, well, they're going to get prion disease all over the place. And that's not the pattern we see. So there are caveats with this model, but it is important because what we're saying here, effectively, is that we might be able to slow the propagation of this protein. So we know, for example, that we can try and do that in a couple of different ways. One is to actively immunize people. That is to say, after you have got your Parkinson's, maybe we could give you something like a vaccine that would stop everyone from getting it. So in actual fact, this is for everybody in the community before you get your Parkinson's. So essentially, we would have an immunization program, just like you have one for polio. And the other approach is to have passive immunization. So this is when you say, well, these patients have definitely got the disease. We know they're going to have this protein. Can we give them something, maybe specific antibodies, that will stop that protein from moving around the brain? Now, that's a much more expensive process because in actual fact, you have to target people and give them the specific treatment at the right time, as opposed to just immunizing everybody. Immunizing everybody is going to be really hard because we don't have a treatment either. There is some work looking at the possibility of how we could do this. But I would remind you, this is all from mice. So the idea of putting in antibodies that will stop the spread of alpha-synuclein tangles and this protein going through the brain is something that we have models for. And there are lots of ways we could do this. We could say, well, look, can we just stop that protein from sticking to itself? Can we stop it from moving from cell to cell? Can we break up the protein? All of those things are theoretically possible. And it is true to say we actually have active clinical trials in play. So these are generally at the moment at a stage where they're looking at safety trials for Parkinson's disease patients. They're not yet available here in Australia. Effectively, what we're saying is these are the first level. Do these drugs behave in a way that is safe in humans? Because sometimes we trial things and patients die because of them. So we have to do the very, very important groundwork. But the idea of targeting this protein is something that has become a very hot prospect. So targeting alpha-synuclein protein. Now I do again have another word of warning, and that word of warning comes from the Alzheimer's world, where for the last 10 years they've had a protein in their cells called amyloid. And they have found really good ways of getting mice clear of amyloid and mice getting better. And when they've put these trials into humans, clears the amyloid, but their Alzheimer's continues to get worse. And we don't really know what the synuclein is doing. It might be there, it might be a bodyguard. It might be protecting our cells and resisting cell death until such time as it can't do anymore. And then you walk into the dead cell and it looks at you all guilty going, oh, who, me? What me? No, I didn't do this. I was just trying to help. It's a bit like that sort of Kevin 07, I'm just here to help. Or no, 2011, whichever one it was. Okay, so what I've done so far is I've told you about all of these things You know, is Parkinson's due to diabetes or energy control, mitochondrial function? Is it due to protein buildup? I didn't have time to talk about immune therapies, with the autoimmunity story, inflammatory story. And you get all these people who are experts, and they get up on a stage and a platform, and one will talk about this, and they'll say, well, this is what causes Parkinson's. Everyone applauds, they walk off. Next person gets up and says a completely different thing. Oh, this is what causes Parkinson's. Everyone applauds, they walk off. And you start thinking to yourself, well, are all these guys wrong? It seems unlikely. They all seem to be quite smart. So then the question is, what if they're all right? What if they are all absolutely correct? Because that's possible. Why is it that, you know, maybe you can't clear the protein from your cell, that needs extra energy, that starts to fall over, and then there's an immune reaction because the cell dies and that fires the next one off. So what we could be looking at is a problem that looks like this. Effectively, we have this issue where Parkinson's pathology is not due to one pathway, and we treat one thing and we say, oh, it didn't really work. Well, in actual fact, it means what we might have done is driven it down a separate pathway. And this is where we need, as doctors and specialists and scientists, to be thinking, how do we understand the whole of the process? Because everyone's Parkinson's may have a different balance of these processes. So I don't want to get you too depressed. As the Chinese say, may you live in interesting times. And we do. Arguably, there has never been a better time to have this disease. The truth of the matter is you don't get a choice, unfortunately. There is lots of exciting research going on. People say there's going to be a cure. I've been hearing there's going to be a cure in the next 5 years for the last 17 years so far. So don't wait. We are seeing formulations, new formulations, reformulations, repurposing of drugs, like a diabetes drug. And these trials are going to come to Australia. I promise you, they're already happening. Okay? So get involved. The future is more than just the dopamine story. We need to have some novel approaches, and it's difficult to know because we don't understand all of the disease. And then the final slide I'm going to put up here essentially is a resources slide. The first one there is the Just Diagnosed slides. The Survivor's Guide is an online video you'll find at YouTube. There's some interviews of me on the It's Not Funny website. And then people asked me last night about where do you find out about trials going on in Australia or internationally. And of course my Twitter handle at the end. Thank you so much.